Right. So evening everyone. Let's see this. The topic is redox reaction. So basically, there are many types of chemical reactions. If any chemical reaction is going through terminologies like oxidation and reduction, and in fact, without oxidation, there is no reduction and vice versa. So it has to happen simultaneously. Such type of reactions are called redox reactions. By definition, oxidation is something where there is a loss of electrons from the species. Or another way of defining is if there is more electronegative elements getting added to the reference species you are talking about, or there is a removal of less electronegative atoms out of that reference species we are talking about. So this fits the definition of oxidation. Similarly, if there is a gain of electrons, removal of more electronegative element, or addition of less electronegative atoms, that implies reduction. Okay. Now, terminologies like oxidation state becomes an important parameter to discuss whether a species is undergoing oxidation or reduction. Okay. Now, what does that exactly mean? See, it is an arbitrarily charge that is developed on an atom when it is removed from all the attachments. Usually, this kind of a definition is more valid for covalent molecules or covalent species. If you are talking about a reference atom, and if that atoms, all the surrounding atoms are being removed, and like to see what is an arbitrary charge that it can gain, that charge is what we call it as oxidation state. And oxidation state could be a real charge or an hypothetical one. Okay, so it is both hypothetical or a real charge which is assigned to an atom after breaking the bonds and shifting the electrons to relatively more electronegative atom. So whenever you shift the electrons, depending upon electronegative difference, whichever is more electronegative, the electrons will shift on to that particular direction, and the other atom would gain a positive charge accordingly. There is two terminologies that we'll use very often. One is oxidation number and oxidation state. 90% of the cases, oxidation number and states are taken as same. Okay. But there is slight difference in understanding of number and oxidation states. See, state is an absolute value assigned for an atom. Got it? While oxidation number is an average of all the oxidation states in that particular molecule or a species. Got it? To elaborate that, let me show you. If at all I have ammonium nitrate, okay, see, ammonium nitrate usually exists in this form, that is NH4 plus and NO3 minus. So now, if I take NH4 plus structurally, it would have four bonds this way: hydrogen, 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 hydrogen with a plus charge on it. Now, nitrogen usually has more electronegativity. If you notice the electronegativity wise, nitrogen is more electronegative than hydrogen, which means nitrogen will gain the electrons from hydrogen. Partially, of course, it is not a ionic bond, it is a covalent bond, but there is a partial movement of charges more towards nitrogen in terms of electrons, which means hydrogen will start losing electrons as well. And even though it is a very partial amount of movement of charge, here we will give a complete charge assignment because you are making it to feel as if it is an ionic bond, and then it is coming out of all the bonds possible. In that case, now nitrogen would have, let's say, X amount of charge on it, which is the oxidation state. Then there are supposed to be four hydrogens, and each is gaining plus one charge. Each is gaining plus one charge. Why? Because it is losing the charge towards nitrogen, and that should be equal to overall. Have you noticed that there is already some plus charge on it? Okay. So that plus charge will always be carried over the entire species. So that means x plus 4 should be equal to plus 1. So x is equal to minus 3. So we say that the oxidation state of nitrogen in NH4 plus is minus 3. Okay. On the other hand, if you notice NO3 minus structurally it is like this: N double bond O minus, and here it has dative bond O. As per chemical bonding, considering if the Lewis structure is been written for it, this is how you can write it down. But dative bonds can always be represented into a simple covalent bond. If you recall, we can write that by simply assigning the formal charges. Can you recall these points, what I said? Just assigning the formal charges, and arrow can be changed into plus and minus. Okay, plus and minus like this. Got it? So both the structures are one and the same. One is represented giving the coordinate covalent bond. The other one is represented only as a covalent bond. Clear? Now, this structure would be more useful for solving purposes. Got it? Now, for this structure, if you notice, I can say something that oxygen is in a way which is more electronegative, so it is gaining 2 electrons towards itself. And here oxygen is also gaining 1 electron. Here oxygen is also gaining 1 electron towards itself. So you could, without solving like a algebraic equation, you could simply say that nitrogen in a way is losing 4 electrons. So loss is always denoted by plus. That means there is loss of 4 electrons, and already there is one more plus on it. So total makes it 5. If you have to write it like an algebraic equation, then I can also write it as x, and it is losing out 4 electrons, so plus 4 here, correct? And uh, this is x charge, sorry, my mistake. X is the charge of nitrogen, and plus charge of oxygen. How much is the charge every oxygen is gaining? See, this oxygen already has minus charge. It must have given one more electron onto it, so I can write it as minus 2. Same goes with this one also, it is also minus 2, correct? And here also, if you notice, this is also minus 2, isn't it? It has minus 2 on it. And overall charge here it is how much? Now, if you notice the overall charge here, it has minus 1, isn't it? So overall charge is minus 1. So from here it is x minus 6 equal to minus 1. So that makes it x is equal to 5. This is solving like an algebraic equation. This is simply checking based on the structure. But one thing we learned, that oxidation state of nitrogen in NO3 minus is plus 5. Now, if at all I write oxidation number of nitrogen, it simply has to be average of these two. Got it? Which is 1. So oxidation number of nitrogen in ammonium nitrate is 1, while oxidation state is 2 oxidation states are possible, minus 3 and plus 5. Okay? Everybody, please make sure you're writing it simultaneously. This is a practice, you need to have it together. Okay. I hope all of you understood what is the difference between oxidation number and state, and also how to figure out based on structure what will be the oxidation state. Clear? Next, there is an important note, you might check it out, that oxidation state is always an integer value. Oxidation state is always an integer value. It could be positive value 0 or -1. But oxidation number may be integer, okay, or fraction. It could be either of that. Clear? This point is clear, everybody. Let me show you with an example, how this point is valid. Check. When it comes to Fe3O4, okay, this is a very common compound which you will come across. Basically, it is a mixed oxide. It is a mix of FeO and Fe2O3. When you mix both of them, you will get Fe3O4. Now, individually, these are two molecules, just like how this salt I split into two molecules here or two species here, and then figured out what is the oxidation state of each nitrogen. Similarly, I'll do the same thing here also. Now, iron has oxidation state here. Let's say, if at all I take iron oxidation state is X plus oxygen always try to make a double bond. That means it will always gain two electrons towards itself and overall is 0, which means the charge on iron here is +2. So this is the oxidation state of iron. While here, if you notice, iron, there are two irons here, 2x plus 3 times of -2. Overall, there is no charge on the molecule, so it is 0. So 2x is equal to 6 or x is equal to +3. So the charge on this iron is +3. For one iron, the charge is +3. Clear? Now, how do I find the oxidation number? Oxidation number will be equal to, there is one iron with a +2 charge. So 1 into +2 charge plus there are two irons each with +3 charge. So 2 into each with +3 charge and divided by how many total we have? 3 iron atoms we have in this case. So therefore, this is 8 by 3. So oxidation number of iron is 8 by 3 in this case. So I hope all of you got this difference. What is oxidation number? What is oxidation state? And oxidation state always has to be integer, while oxidation number could be anything, fraction, integer, anything. Okay, right. Everybody has made a note of this. Good. Now, let's understand what are the rules pertaining to oxidation state or oxidation number. If at all I have to figure out which element would get more, I mean, it would have more gaining towards positive side or more gaining towards negative side in terms of the oxidation charge which it attains, then look into it. Oxidation electronegativity of the elements becomes the main basis on which you can figure out what is the oxidation state. This is a general electronegativity series which everybody must be learning. Okay, you should be able to remember this order. Got it? That is, fluorine is the most electronegative element which you are aware of. Fluorine is the most electronegative element. Then oxygen, then chlorine, then nitrogen. Okay, chlorine and nitrogen almost have the same value. Chlorine slightly on the upper hand. 3.17 is chlorine and 3.0 is nitrogen. Got it? And then comes bromine, 2.8. Then comes sulfur, almost 2.7, basically close to 2.8. And iodine also has 2.7. And then we have carbon. Okay, in fact, we have selenium also, which is almost the same. Okay, then we have phosphorus, phosphorus is 2.4. Then we have hydrogen. In fact, we have others also, but hydrogen becomes important element that you need to remember. So after hydrogen, then we will get, after hydrogen, we will have boron, correct? Then we have beryllium, correct? Then we have lithium, then sodium, and all the way up to cesium. Okay. So this is the electronegative order that you should know. Okay. Mainly, if you ask me, first five are extremely important here. First five you should definitely remember how the electronegativity goes. And thereafter, check out one thing. You know, carbon and phosphorus would be slightly more than hydrogen, and hydrogen, anything after hydrogen is except for boron, which is non-metallic nature. Rest all are metals. Okay. So it is like hydrogen is acting like a barrier between metals and non-metals. Majority of the non-metals will be greater than hydrogen, and all the metals will be less than hydrogen. Clear, everybody? That's a very important point to understand. Okay. Now think about it, everyone. Fluorine can always, participate in covalent bonding with only sharing one electron. Is that right? That means fluorine can only make one bond. It does not make double bond, triple bond, and so on. Now imagine if it is making only one bond, because fluorine is more electronegative. When you make any bond with any of these elements, fluorine is the only one which will always win the electron because it is the most electronegative. Correct? So this can be standardized that fluorine's electronegativity always remains -1 in a compound. In a free state, it's different, but in a compound with other elements, it will always remain -1. Clear? Likewise, if we compare oxidation state of alkali metals, what are all the alkali metals, everybody? Lithium, sodium, potassium, rubidium, cesium. Okay. Now, these are all alkali metals, and pseudo-alkali, pseudo-alkali, which means which will be behaving like alkali, correct? That implies NH4 plus and thallium plus. These two will also try to showcase +1 oxidation state most of the time. NH4 as a whole, it is a pseudo part. Got it? So whenever there is NH4, you should understand that overall it will always have +1 charge. Got it? Hence, you see, all these elements will only exhibit +1 because they always fall under the last um, uh, last atoms or species in the electronegative series, and anything less than hydrogen, and they can only give one electron, right? Majority of all of them will form ionic compounds, and they readily give away one electron. Likewise, alkali earth metals, if you compare, which is beryllium, magnesium, calcium, strontium, barium. Got it? So if you compare these elements, they usually give you +2 oxidation state because majority of them will follow ionic bonds, and in the ionic bond they will completely give away 2 electrons to the opposite species. Clear? These are kind of fixed. Fluorine always will have -1. Group 1 elements will always have +1. Group 2 will always have +2. The next hierarchy, and also remember the lines which I'm writing is on a hierarchy basis. This is how you need to check out the hierarchy of the elements as well. The next one being hydrogen. The oxidation state of hydrogen will be +1, correct? But it is with non-metals. It will be -1 when it is connected with metals. So if it is with metals, always assume that hydrogen will have -1 charge. Accordingly, the other elements will have. Okay. You can see here, sodium will always have +1, that automatically makes hydrogen as -1. Calcium always has +2, that makes hydrogen as -1. Clear? So if you have something, any metal which is unknown to us. Let's say there is some element like this. Okay, sorry, chromium, CrH3. Right? If this is given to us, and I need to know what is the oxidation state of chromium. In such cases, you will always take hydrogen as -1. Got it? So in that case, the charge would be how much? +3 in this case. Got it? So this way, whenever it is connected to metals, it will always possess -1 charge. If it is connected to non-metals, okay, anything other than these metals, suppose if you have water, okay, in water, it will lose one electron to this oxygen from here and this end. So that makes oxygen will have -1 and both these hydrogens will have +1 oxidation state. Everyone, have you written? Okay. You slowly need to start, sinking water, first group elements, second group elements. Understood? What is their oxidation states? And when it comes to hydrogen, it will have -1 and +1 in the compounds. Okay. Next. Oxidation's number of any free element is always equal to 0. Okay. Either you take an elemental form or a simple atom also. See, O2 is the elemental form of oxygen. That means as an element, it will always be observed in nature as O2. Fluorine is observed as F2. Cl2, chlorine is observed as Cl2. Zinc is observed as a solid metal. Copper is observed as a solid metal. So all of these are elemental forms. The elemental form of these uh, atoms is always equal to 0. The oxidation state is always equal to 0. Okay, whether it is P4, S8, aluminium, or O3, ozone, these are also elements only, oxygen atoms only. So there is no electronegative difference. Hence, their oxidation state will always remain 0. Got it? Next, maximum oxidation number of an element will be its group number in the periodic table. Okay, or minimum oxidation state is 8 minus maximum oxidation state. Okay, because in certain cases you could have uh, multiple oxidation states observed, and this is typically valid for p block elements. Okay, what I'm trying to say is that when it comes to nitrogen can show +5, while when it comes to phosphorus it can show +5 and +3 also, right? So here you can notice the maximum oxidation state of this oxidation state is the uh, what is its group number. Acha, group number is actually 15, but how come it is 5? Basically here group number is with respect to the representative elements, and you know that how representative elements are shown with subgroup as A, correct? So this will become 5A, isn't it? So basically, when it comes to these two belongs to 5A group, correct? Same way, when it comes to oxygen can exhibit, you know, uh, +2 as well as -2, while sulfur can exhibit -2, +2, and +6. Now you notice this can show -2 also, +2 also. Here it can show -2, +2, and +6 also. +6, if it is highest oxidation state, 8 minus 6, it will show +2 as well. Correct? And these belongs to 6A group elements. Got it? So on a hierarchy basis, the first 6 you should understand, in which case what type of oxidation state, which is permanent or which can be calculated. Next, oxygen is present in -2 oxidation state except in the following. Now notice what is the oxidation state in all of these cases. Here, if oxidation state of oxygen is X, plus 2 times of minus 1 because fluorine is fixed, that is equal to 0. So here it is plus 2. Okay. So this is oxy difluoride. This is oxy difluorine or difluoride. Similarly, here if you notice, there is 2x plus 2 times of minus 1 equal to 0. So 2x is equal to plus 2 or x is equal to plus 1. So this is, you know, dioxy difluoride. Okay, this is dioxy difluoride molecule. So here you can notice oxygen in fact has plus 2 oxidation state as well as plus 1 oxidation state. In fact, these are the only two compounds where oxygen can show plus oxidation state, because only when it is connected to fluorine it can lose the electrons. Otherwise, it is the second most electronegative element. Similarly, if it is peroxide you can assess both by structure as well as the oxidation state. See, if you have it like this, you can clearly make out that between these two there is no gain or loss because both of them are oxygens. So only gain that oxygen gains is from this hydrogen. Here also it gains from this hydrogen. So one gain of electron makes it minus 1. Here also this will become minus 1. Well, if you do not know the structure, just simply write it as 2x charge plus 2 hydrogens which has plus 1 charge overall equal to 0. So that makes it hydrogen is equal to minus 1. Okay. Similarly, here also KO2 will always remain as K plus and O2 minus. And here this will have 2x is equal to minus 1. So that makes it x is equal to minus 1 by 2. And here KO3, we have K plus and O3 minus. Similarly, you can see here 3x is equal to minus 1 and x is equal to minus 1 by 3. Okay. I will write one more. I forgot to write that. Okay. If you have Li2O, Li2O, I will have 2 moles of Li plus and O2 minus, and here you can notice that the oxidation state of oxygen is minus 2. When oxidation state of oxygen remains minus 1 in a molecule, you call that as a peroxide. And if it is minus half, you call it as a superoxide. And if it is minus 1 by 3, you call it as ozonide. And if it is minus 2, then you call it as oxide. Very important terminology, everybody. Please do remember what is the names of uh, various oxide forms. Got it? When do we use the term oxyfluoride? When do we use the term peroxide, superoxide, oxide, ozonide, and oxide? Clear? Make a note, everyone. Done? Right, let's go ahead. Check. The total oxidation number due to every element in a compound is the charge present on the molecule. This is a general element. If you do not have, if you are unaware of what is the charge of an element, then you use the above laws, you check out the above rules and put them and try to figure out what is its charges. Like I said, it as a common oxygen will always exist as oxide form. That means it will usually take minus 2 charge. Okay. So consider that into this account. Imagine if I want, suppose to get what is the charge on uh, chromium. So what will I do? there are two potassiums with +1 charge, plus there are two chromiums with X charge, plus there are 7 oxygens with -2 charge, that should be equal to 0. Correct? So that will put X is equal to, or 2X is equal to 12, and X is equal to 6 plus 6. So the oxidation state on chromium is +6 in this case. Similarly, if I want to calculate for sulfur, I will take X plus there are 4 oxygens with -2 charge, overall equal to -2. So that makes it X is equal to +6. So here also sulfate is at +6 oxidation state. Similarly, just by using the rules, if at all I have to calculate for nitrogen, I will write it as X plus 4, each having +1 charge, overall equal to +1. So that makes it X is equal to -3. Okay. Remember, it is the oxidation state which mainly gives the naming, in fact, the suffix naming of all the compounds. Got it? I guess all of you are aware of this. Yeah. Now, what if I need to find out oxidation state of various elements which are marked here, considering oxygen is having a fixed oxidation state which is -2. Consider that in all the cases and try to figure out what is the oxidation state of each of them. Got it? So first let us work out in a column wise. First we'll work out on this column, then on this column. Anybody who has done it already, please take it as a practice. It will be important to remember, recall what is the charge on every element as well. Okay, clear? So let's start working, everybody. See, what will be the charge here now? Check. Nitrogen is at X plus there are 3 oxygens, each would give you -2. Overall charge is -1. So that makes X is equal to +5. Next, X plus 2 times of -2, overall charge is -1. So that makes X is equal to -3, +3. Sulfate we have just learned, S is equal to 6. Sulfite, X plus 3 times of -2, overall equal to -2. So that makes X is equal to +4. Oxalate, okay, 2X plus 4 times of -2, overall charge is equal to -2. So 2X is equal to 6. So X is equal to 3. Permanganate, X plus 4 times of -2, overall charge is -1. So that makes X is equal to +7. Please check if everybody got the left side. Yeah, sure, Ishman. No worries. If one you would do this left ones, right? This is done, beta. Right. See the next one. Here, manganate will have X plus 4 times of -2. Overall charge is -2. That makes it X is equal to 6. Dichromate, 2X plus 2 into 2X plus 7 times of -2 equal to -2. So X is equal to 6. x plus 4 times of minus 2 equal to minus 2. So x is equal to plus 6. Here 2x minus 6 equal to minus 2. So 2x is equal to 4. So this is 2x is equal to 4. So x is equal to 2. Next, here you can see 4x minus 12 equal to minus 2. Okay. So 4x is equal to 10. So x is equal to 5 by 2. Whatever we are calculating is the oxidation number. Okay. Because here, when you are getting this as some fraction, that might be it is a mix of two different oxidation states. And what is that? We will go ahead and learn it. Okay. Don't worry about that yet. Here we are trying to figure out as an algebraic sum, what do we get? Okay. Phosphate, in phosphate, x minus 8 overall equal to minus 3. So x should be equal to plus 5. So I guess these two columns are clear. Right, good. See the next one. If you notice this last column, so here we will have x minus 6 equal to minus 1. So x is equal to plus 5. Here x minus 8 equal to minus 1. So x is equal to plus 7. X minus 6 equal to minus 1. So x is equal to plus 5. X minus 4 equal to minus 1. So x is equal to plus 3. X minus 2 equal to minus 1. X is equal to plus 1. Lastly, in hydroxide, x plus 1 overall equal to minus 1. So x is equal to minus 2. Okay. These are all the typical oxidation states of individual element in a species. Generally, there is a standard rule for group 15 to group 17. Okay, so that is group 15, 16, 17 elements. When they are connected with metals, okay, they usually have a fixed oxidation states. Got it? Like when nitrogen and phosphorus are connected with metals, they would always have a fixed oxidation state of minus 3. Sulfur will show a fixed oxidation state of minus 2, and halogens will show a fixed oxidation state of minus 1. Okay. Whether you know the information of the metal or not, you should be able to figure out the oxidation state of metal. Okay. For example, in this case, if you notice, manganese, we know that, sorry, magnesium. Magnesium, we know that it is plus 2. So that automatically makes nitrogen as minus 3. Here, phosphorus is minus 3, hydrogen is plus 1. Sulfur is minus 2, hydrogen is plus 1. Chlorine is minus 1, hydrogen is plus 1. Sodium is plus 1, fluorine is minus 1. Okay. These are all the oxidation states. Of course, there are few exceptions also like this. FeS2, if you notice, correct? The structure is slightly different here. Basically, here sulfur and sulfur are connected by a bond. And then it is having a minus charge on both the ends, which is being supported by iron plus 2. So this is the structure of iron pyrite. Okay, also known as fool's gold. Okay, fool's gold, very important words. This would be coming across the question directly. Instead of directly giving it as iron pyrites, you will be asked, I have taken 10 grams of fool's gold and then blah blah blah, calculate the oxidation state, calculate the equivalent weight. These kind of questions will be coming across. Okay, so remember the terminology: iron pyrites or fool's gold. The oxidation state, now this is how the structure would be. So sulfur has minus 1, this sulfur also has minus 1. These are its respective oxidation states. and iron has +2 oxidation state in this case. Okay, next. Oxidation state of any ligand present in a complex is the charge present on its species itself. Got it? Lot of time we need to figure out what would be the oxidation state of metal in a complex. For example, a very standard question which has been asked in JEE, I'll just push that here. Check. This is how it is been there. N, chromium, NO2, then we have O2 like this. Got it? I have an O2 group here. Then I have chlorine 3 times here like this. Got it? 3, 4, 5. Okay, one more I forgot. H2O. Right. So this is how we have. And on this complex, there is an overall charge. Correct? So how much it is? Right. So overall charge is being -2. Okay. So either you will be given it as -2, or you would be given this way. That is K2. Something like this is given. So when you have to calculate the oxidation state of chromium in this case, for example, I need to find out what is be the oxidation state of chromium in this case. In that case, you need to check out what were the individual oxidation state of each and every species in here. Now, these groups which are present along with the metal inside the bracket, correct? These are called ligands. So these are all called as ligands. Now, ligands can be positive, ligands can be neutral, positive, or negatively charged. But here it is not given what is the charge on it. You have to know what is the charge they are carrying. Got it? And that's what we are trying to figure out. Ligands, what is the charge they carry? Let's see. If at all I have NO2 minus or NO3 minus, I mean NO2 or NO3, automatically overall species will always carry -1 charge. Got it? Nitrogen, when it is present as NO2 or NO3, it meant that it is always carrying -1 charge. Suppose if at all I have sulfate, SO4, it is automatically carrying minus charge. If it is only ammonia, it is carrying 0 charge. Carbon monoxide is carrying 0 charge. Water is carrying 0 charge. If this is the ligand given, EDTA, ethylene diamine tetraacetate. Going ahead, we have a lot of details to learn about it. As of now, don't worry about what is the entire name of it. Okay, remember it just as EDTA. EDTA is given means you should back of the mind know that its overall charge will always be 4 minus. Okay. Similarly, when you have oxalate C2O4, automatically you should know it is 2 minus. Carbonate CO3, it should always be 2 minus. Every halogen is given in this as a ligand. That means it will carry -1 charge. If OH is given, it will carry -1 charge. Now, this is interesting. If single oxygen is given, you'll always take it as -2 charge. Okay. And if O2 is given, in a bracket it is given, usually it could be either -1 or -2. Now that is difficult to figure out whether it is -1 or -2. That depends upon the stable state of the metal. Like chromium's oxidation state is, the most stable oxidation state is +3. So if you are getting +3 with O2 as -1, that means it is a peroxide, it is a superoxide. If you are getting +3 with O2 as -2, that means this O2 is peroxide. Understood? If bracket is not given, that means it is definitely simple oxide and its charge is -2. Is this point clear with oxygen? Got it? So oxygen is slightly difficult to judge. So just we have to be careful with the complex given. Okay. Now let me put that value. Let me put this understanding here to figure out what is the oxidation state of chromium in this case. So to figure out that, first, everything that is present outside the bracket, you remove them as ions. Like you can see there are 2 potassiums. I can make them as 2K plus. And since this got 2K plus, the overall charge here should be -2. Because 2 potassiums make it +2 charge. So the overall complex should have -2 because when you combine both of them, it should appear neutral. Hence, now the oxidation state of chromium is X plus NO2 is -1 plus let me take O2 as -1 as a superoxide and judge. Then I have plus of -3 because each chlorine will be -3 plus water is 0. So that is equal to -2. So how much we are getting? X is equal to x minus 5 equal to -2. So x will be equal to how much? Plus 3. So this is clearly showcasing that here O2 minus is what? It is superoxide. Here this is superoxide. It is not a peroxide, it is a superoxide form. Clear? Right? Similarly, if you have cyanide Cn will always carry -1 charge. SCN, thiocyanide, again -1 charge. Got it? You can write it in any forms here. You can write it as NCS also. It is still -1 charge. Got it? They all will carry -1 charge here. There is one more term called as DMG. Okay? Dimethyl glyoximate. Even if it is not given, you'll always take it as -1. Okay? Acetate, CH3COO. It will always carry -1 charge. Any acidic group with a -1 position. So phenoxide, PHO will always carry -1 charge. Okay. So these are other few ligands which will be useful. Going ahead, we will have a complete topic on that. So don't worry about it right now. As of now, these common ones which are most used like nitrate, sulfate, oxalate, carbonate, EDTA. These are the most common ones. Of course, halogens. Okay. These are most common ones. So if you notice these common ones coming across anywhere, especially in problem solving for equivalent weights, you should know the charge there. What is the charge they are carrying? Okay. Now notice carbon monoxide has zero charge, which means iron here is X plus 5 times of 0 overall equal to 0. So X is equal to 0. So yes, iron will have zero oxidation state when it comes to FeCO5. Similarly, when it comes to iron here, X plus 6 times of cyanide will have -1. Overall charge is -4 because if I separate 4 potassiums, this will get plus -4 here. So that makes X is equal to +2. So that is the oxidation state of iron in this case. Clear? So I suggest everybody please go through the point 10. Okay, write it in your own words, make yourself comfortable. What is the charges of every species here? Okay, I'll give you a minute's time. Get it done. First one. Here oxidation number would be 3x plus 1 equal to 0. That makes x is equal to -1 by 3. That is the oxidation state on oxidation number on nitrogen. Next, here this is the same as KMnO4. Here x plus 1 plus 4 times of -2 equal to 0. That makes x is equal to +7. And here also same thing. 2x plus 7 of -2 equal to 0. So x is equal to +7. Cl2 here, x plus 2 times of -2 overall equal to 0. So x is equal to +4. HClO3 here. So x plus 1 plus 3 times of -2 equal to 0. That makes x is equal to +5. This is same as ClO4 minus. So here x we got it as +7. And here only sulfate is -2. That makes iron as +2. Correct? And here also only sulfate is -2. So 2 times of x plus 3 times of -2 overall equal to 0. So 2x is equal to 6 and x is equal to +3. This is for sulfate. KMnO4 we learned x is equal to 7. K2Cr2O7 we learned x is equal to 6. Na2S2O3 we learned it as S2O3 2 minus where x is equal to how much? 2. Okay, and here we learned x is equal to 10 by how much? 10 by 4. Okay, so please check this out. Those who have the notes can continue. Otherwise, those who don't have it, please quickly finish this and let me know. We can go ahead. Check the next row once quickly. This one also we worked out. X we found it as plus 5. This also we worked out. X is plus 7. This also we worked out as phosphate, where x is equal to plus 5. This also we worked out. X is equal to plus 5. Here hydrazine. See, in hydrazine we have NH2 and NH2. This is how they are connected. The name is hydrazine. We'll be using very frequently going ahead. So remember that. So based on structure, I can clearly make out that each nitrogen will have -2 and -2. And as a algebraic sum also, you can see 2x plus 4 equal to 0, and each nitrogen will have -2 charge. And here x plus 3 -2 overall equal to 0. So that makes x is equal to -1. This is also very frequently used, known as hydroxyl amine. Hydroxyl amine. Okay. N2 is 0. pH3 is -3. X is equal to -3. This also we learned. X is equal to 8 by 3. Okay. This we just can figure out easily. X is equal to 3. H2SO4 we learned. X is equal to 6. Here x plus 1 minus 2 equal to 0. So x is equal to plus 1. And here x is equal to plus 3. And here x is equal to plus 3. And here also arsenic will have x is equal to plus 3. Okay. Why? Because sulfur will show -2 oxidation state with metals. So we can see 2x minus 6 equal to 0. So x is equal to plus 3 here. Okay. While here x will be equal to plus 5. Got it? And here x is equal to, you can see 2 times of plus 1 plus arsenic is x plus 3 times of -2 overall equal to 0. Correct? So x is equal to 3 again. X is equal to 3. Cu2s, so 2x minus 2 equal to 0. So x will be equal to plus 1. This is the copper's charge. And this also we learned. Nitrogen, this has -3 and plus 5. Ammonium will always have -3 on nitrogen here. Sulfur will be plus 6. Here manganese will be plus 7 because it is from a manganate form, and lead will be, right, lead will be plus 2. Here same logic as that of iron, so x will be equal to 8 by 3. Okay. And here N3 minus, okay, this is one thing I forgot to add. Everybody go back here and add that. Okay, N3, okay, N3 is very important compound. N3 minus, like this. Okay, subscript 3, this is called azide. This is called azide. Azide will always possess -1 charge. If only nitrogen is given and 3 minus is above, that means it is nitride. This is nitride. So understand the difference there. Where is N exactly? Okay. I hope all of you understood this difference. Yeah. Everyone, you got this? Now, come back to these cases quickly. So, azide is actually -1. So, that makes x minus 2 equal to 0. So, x is equal to +2. So, that is the charge on lead. And what is the charge on nitrogen? Charge on nitrogen here. Charge on nitrogen will be equal to -1 by 3. Got it? So please check this page if everybody has got these cases clearly. The last few of them. Here, chromate, we learned it as it will always come out to be +7, as nitrogen here will be -3. I3 minus, okay, I3 minus, we will have x minus 3 equal to, sorry, 3x. 3x equal to -1. So x is equal to -1 by 3. Okay. And here bromine, x minus 5 equal to 0, x is equal to +5. Iodine, here we learned it already, x is equal to +5. ClF2 minus, so x minus 2 overall equal to -1, so x is equal to +1. Now notice what is the charge on iron. Suppose if at all I have to figure out what is the charge on iron here. Okay. Now it depends upon whether you're talking for 1 mole or 0.93 mole. See, this is how you write down 0.93. Here I am writing it for 1 iron. So for 1 iron, how much will be the charge? -2 equal to 0. So x will be equal to 2 by 0.93 or 200 by 93. So that is the oxidation state. Iodine, x is 0, oxidation state is 0. Here x is equal to +1. Okay, so please do check these cases. Done? Now, check it out. Next thing what you need to know is based on the Lewis structures. These can be only determined based on the structures known. Without structure, it becomes difficult. One or two, you can guess it out, but without structure, you do not know every element's oxidation state here. Okay. So in that case, how do we figure out? Now, this is something which we already learned. When you have an electronegative difference, let's say A and B atoms have electronegative difference where B is more. If I write single line, that means B will have -1, A will have +1. If you have a double line, that means B is gaining 2 electrons, A is losing 2 electrons. Same way here. If B is equal to -3 and +3, this is how we can write down. And if I have a dative bond here, correct? So suppose if the dative bond is given like this, clear? So between A and B, the dative bond is same as writing as, A getting plus and B getting minus. Okay, clear. So now again B is being more electronegative, so the electrons will go on to that. So what is the charge on A? A will have plus 2 charge and B will have minus 2 charge. So in case if you have an arrow like this, A to B arrow, that means the charge on A is plus 2 and the charge on B is minus 2. Got it? And check. HNO3, the structure is like this. N, I think I discussed this already. N double bond O, O and H with a dative bond O, which can also be written as N, O and H with a covalent bond with minus and plus. And this minus and plus will help more easily understanding the bonds. So I told you that here there are two electrons being pulled by oxygen, one electron here, one electron here. So now notice the charge on nitrogen here. So nitrogen already has one plus one charge. It is losing two electrons on the left, one above, one below. So that's how it becomes total plus 5 charge. So that is the charge of nitrogen in HNO3. Azide, the N3 minus was azide. If it is with hydrogen, this is called hydrozoic acid. Hydrozoic acid. And notice hydrozoic acid, H will be connected with nitrogen, which is having a double bond nitrogen and double bond N. This is the structure of hydrozoic acid with plus here and minus here. Got it? So for this case, now notice what is the oxidation state on each of them. How do we check? See here, nitrogen is gaining one. That's it. There is no other gain or loss from the other end. So which makes it, this nitrogen has minus one. And this nitrogen has plus one. And this nitrogen has minus one again. So these are the oxidation states of respective nitrogens. Clear? HNO3 and hydrozoic acid. I hope all of you understood this part. Next one is hypo. See, in hypo, we have structure like this. S, basically, it is a sulfate type of structure. Imagine like this. S double bond O, double bond O, O minus and O minus. What do we call this? This is called sulfate, isn't it? This is sulfate form. Now, if this sulfate, is such that we are replacing one of the oxygen here with sulfur itself, then the name would be slightly different. Now we call it as thiosulfate. That's the only difference. Okay, now this will become thiosulfate because now that oxygen has been replaced by sulfur. Got it? Now here is the interesting part. Between these two sulfurs, the character is different. Reason being, whatever the oxygen's qualities are possessed, that is being replaced by sulfur. Okay. In fact, if you notice the sulfur has, two lone pairs and one sigma bond. One is pi bond. Out of two bonds, one will be sigma, one will be pi. So that makes this sulfur as one sigma and two pi bonds, or two lone pairs. One sigma and two lone pairs corresponds to sp2 hybridization. And this sulfur, if you notice, it has four sigma bonds. 1, 2, 3, 4. See, pi bonds never account for hybridization. But as per sigma bonds, it is supposed to be sp3 hybridization. And you know that electronegativity wise, sulfur, which is sp2 hybridization, will have more electronegativity than sulfur with sp3 hybridization. In fact, any sp2 hybridization, let me write down directly. If you have any sp2 hybridized orbital, that will always have more electronegative than sp3 hybridized orbital. Therefore, between these two also there is an electronegative difference. So check who is winning the electrons in that case. That means this sulfur is winning 2 electrons here. Here oxygen is winning. Here oxygen is winning 2. Here oxygen is winning 1. And that's how, if you calculate the oxidation state on this sulfur here, we will have +2, +1, +1, and +2. That makes it +6. So the oxidation state of sulfur here is 6. Now, similarly, if I take the oxidation state here for this sulfur, you will see we will have simply -2, because -2 is the only gain that you can see it. Correct? So the oxidation states of two sulfurs are different here. One is -2, one is +6. Very important. In thiosulfate, what are the oxidation states, everybody? Did you all make a note? Right. Similarly, if it comes to this one, S4O6, okay, so basically here it is 2Na plus S4O6 2 minus, and S4O6 2 minus will have a structure like this. When you have way too many sulfurs, always make single bonds this way, and only at the corners you will start contributing towards oxygens. To keep it more uniform, I'll put it as 3 oxygens here and 3 oxygens on this end, like this. So that satisfies the structure. And hybridization of every, because you can see the lone pairs on this sulfur, there are 2 lone pairs here, 2 sigma bonds, 2 lone pairs, 2 sigma bonds. So that's why, if you notice the hybridization, whether it is this one, whether it is this one, whether it is this one, all of them has only one type of hybridization, which is sp3 only. All of them show sp3 hybridization. And since they are showing sp3 hybridization, that means there is no electronegative difference between them. Thus, there is oxidation state here being 0 for this one. For this it is 0, for this it is 0. But for this sulfur, it is 2 loss towards oxygen here, 1 loss here, and 2 loss here. Okay, so that makes it +5 oxidation state. Same way here also, you can see, here also you can notice. So there are 2 loss here, 1 loss on this side, and 2 loss on this side. So that makes it +5 oxidation state. So in this particular type of sulfate groups, right, you have uh, two sulfides with +5 oxidation state and two sulfurs with 0 oxidation state. Okay, this kind of compounds are known as thiones, and there are 4 of them. So this is called sodium tetrathionate. It's called sodium tetrathionate. Okay, everybody, please make sure that you are clear with the structures of these two. Right. See the next one. In case of organic compounds, right? Organic compounds, we just have to write the overall structure and see what is the oxidation state it is carrying. For example, here we have carbon with 3 hydrogens connected to it, and then it is connected to oxygen, then hydrogen. So simply check out the gain and loss here. So with respect to hydrogen, it will always be gain, and with respect to oxygen, it will be loss. So that's how carbon will have -3 gain and +1 loss, which makes it -2 oxidation state on methanol. So the name is methanol. Next. CH3 C double bond O NH2. So again, there are two types of carbons here. So three hydrogens on this carbon. Then there is a double bond O, and then we have nitrogen with two hydrogens. This is the structure we have. So gain and loss wise, here you can notice nitrogen is uh, losing towards carbon. Here also it is losing. Here also it is losing. While here nothing will happen between these two. But carbon, when it comes to here, it is losing out to, and it is losing out to nitrogen based on electronegativity. Thus, if you care for this carbon here, check out oxidation state is -3. And for this carbon here, it is +3 because it is two losses, total three losses on right hand side as well as upside. Okay. So these are the oxidation state. So this is simply acetamide. Acetamide. Okay, as of now, I'm more because this is a terminology used in our question. So that's why I'm using this terminology. IUPAC name is different. Okay. IUPAC name is ethanamide. Yeah. Next is, this is acetic acid. Very, very useful, and we use it a lot of times in this redox reactions. So remember acetic acid. Again, here also we have three hydrogens connected with C double bond O and OH. So you can see three gains from three hydrogens. There are two losses here, one loss here. So that makes this as -3 and this as +3. Okay. Same as the acetamide case. Same here also, which is very, very similar. We have three hydrogens here with carbon having triple bond N, which is very, very similar to what we have done the cases here. So for these three, and here there are three losses only. So here it is becoming -3 and here it is becoming +3. Okay. Okay. So the common name used here is methyl cyanide. So I guess this structure based cases so far, whatever we have done is clear. Okay, I'll give you a minute's time. Please go through them. Suppose I have CrO5. Okay. If at all I go with the traditional algebraic equation, so I would be writing it as x minus 10 equal to 0 and x is equal to 10. But actually, this is exceeding the maximum oxidation state which chromium can actually attain. Chromium can maximum attain 6 because in its outermost shell, the configuration of chromium being 4s1 and 3d5, it could maximum lose 6 electrons only. So it can never have +10 oxidation state. So that means, although as an equation it looks correct, but it is an absurd value. Why this might be happening is because here oxygens, you are considering them as oxides for all of them. But it might so happen that some of them might be simple oxides and some of them may be peroxides. And whenever there are peroxides, there will be peroxy linkages. Okay. So if you have peroxides, everybody, there could be peroxy linkages as well. Clear with the thought, everyone? Right. Now notice, if at all I say there are X atoms of oxygens which is in the peroxide form. Suppose if there are X amount of oxygens which are present in a peroxide form, then how do we figure out, how many number of peroxy groups we have? See, then what you do, keep doing along with me, everybody. Check. Write this way. Cr. Imagine there are X number of peroxides which leaves, 5 minus, there are total 5 of them, right? So 5 minus X has only oxides, correct? And chromium can maximum attain 6. So you always go with maximum state. So plus 6, that is a maximum state, plus, sorry, like this, yeah, plus 6, plus there are two oxygens which are peroxides. Peroxides will have minus 1 charge, not 2, X oxygen. X oxygens which has minus 1 charge, plus 5 minus X which has minus 2 charge, and overall charge is nothing, which means 0. So that makes it X minus X and minus 10 and plus 2X, that should be equal to 0. So X minus 4 equal to 0. So X is equal to 4, which means number of peroxides, in CrO5 is equal to 4. Okay. And number of oxides in CrO5 would be equal to 1. There is only one oxide present. Okay. Now, every time there is a peroxide, two oxygens will make one linkage. Okay. For every two peroxides, there exist one peroxy linkage. Okay. That's how you can write the structure now. Chromium will have C double bond O, like this. We'll have O and O this way, O and another O this way connected. Now you can see this is one peroxy linkage, this is one peroxy linkage, and these are all peroxides which with each having minus 1 charge, and this one is an oxide which has minus 2 charge. And chromium, you can see it is losing 4 electrons to peroxides and 2 electrons to oxide. So that makes oxidation state as plus 6. Correct? Clear? So this is tetraperoxy chromium oxide, also known as butterfly oxide. Looks like a butterfly shape, so it's called as butterfly oxide, CrO5. Very important compound. Everybody check it out. How to figure out how many number of peroxy groups we can have. Go with the maximum oxidation state which an element can attain. Based on that, you can figure out what could be the number of peroxide as well as how many peroxy linkages it can possess. So in this case, how many linkages we have? Because there are 4 of them, so peroxy linkages are 2. Right? So there will be 2 peroxy linkages. Okay. Finished? Now, if you have understood that, please apply the concept for NO4 minus and try to figure out how many peroxy linkages we have and how many oxides we have. Peroxides how many and oxides how many we have. Nitrogen being from group 15, maximum oxidation state it can get is plus 5, correct? So go with that logic.
तो थोड़ा ऊपर जा सकते हो।
हाँ जी।
बस बस।
to get two peroxides. No, I guess two peroxides. Okay, and linkages one. Hmm? Hmm. Right, everybody, please check. So same way we can do it for here. So 5 plus, let's say there are X number of peroxides. So that leaves behind 4 times of, sorry, there are 4 minus X times of minus 2, which is simple oxides. That should be overall equal to minus 1. So we have 5 minus X minus 8 plus X overall equal to minus 1. So X minus 3 equal to minus 1. So X is equal to 2. So there are two peroxy linkages. So, sorry, two peroxides, two peroxides with one peroxy linkage. And that's why the structure would be N double bond O with one being O minus, the other one being OO minus with plus here, this way. This is the structure of NO4 minus, okay, known as peroxynitrate. This is peroxynitrate. I guess all of you has got that, right? Check next one. S2O82 minus, selenium. Selenium is an element falling under the oxygen group itself. Oxygen, sulfur, selenium. Okay. So just to refresh your memory, group 16 elements include oxygen, sulfur, selenium, tellurium, polonium. These are the elements. Okay. So since we are discussing about selenium now, so do the same thing here. 2 times of what is the maximum oxidation state selenium can take? 6, because it is coming from an oxygen family. 6 is what it takes. So 2 times of 6 plus x times of minus 1 plus 8 minus x times of minus 2 overall equal to minus 2. So 12 minus x minus 16 plus 2x equal to minus 2. So x minus 4 equal to minus 2. So x is equal to 2. Okay. So again, we are getting two peroxy linkages. Sorry, two peroxy oxides or two peroxides and one linkage. So that's why selenium with oxygen, oxygen with another selenium with double bond O, double bond O, O minus, double bond O, double bond O, and O minus. Clear? So name is peroxy diselenate. Peroxy diselenate. Usually, linkage is the question that has been more frequently asked. How many linkages it has? So, linkages is 1. Now, this is about H2OH2 minus. Next one is H2SO5. Now, I'm directly writing the structures. You know how to do the working already. So, check out S, double bond O, double bond O. One is OH, the other one is OOH. We can see one peroxy linkage. Here we have one peroxy linkage. Got it? The name is peroxy monosulfuric acid because it is still an acid form. So that's why it is monosulfuric acid. But it is peroxy form. So peroxy monosulfuric acid. The industrial name is Carose acid. Okay. Industrial name is Carose acid. H2S2O8 structure is S double bond O, OH double bond O. Just like how we write selenate, same way here, sulfate. So OH. And since it is in an acidic form, we write it as peroxy disulfuric acid. And industrial name is Marshall's acid. So remember these two names, Caro's acid and Marshall's acid. This one is benzoic acid. Again, this is one acid which will be coming very frequently in this topic. So, in benzoic acid, you will have a benzene group connected to COOH. So, you can simply check carbon is losing one electron here, two electrons here. So, that means the oxidation state here is +3. Similarly, this is called aniline, an important base, organic base. So, same way, nitrogen will gain one electron from this carbon and gain two from two hydrogens. So that makes it -3 oxidation state. Okay. So in aniline, nitrogen has -3 oxidation state. Next, here C6H5NO2. This is nitrobenzene. So basically, same thing we have. C6H5 is benzene structure, and then we have nitrobenzene. That is N double bond O, O minus and plus. Now, oxidation state of nitrogen here implies it is gaining electrons from carbon also, but losing towards oxygen and losing towards this oxygen. Okay, so it has -3 +3 losses and -1 in a gain, but also has one plus charge on its own. So that makes overall charge as +3. So +3 is the charge on nitrogen oxidation state. While if you notice the same thing in aniline, we have already did that. In the case of aniline, N, H and H here. So it is gaining one from here and one from here. That makes it overall -3 oxidation state. This was just asked this year in JEE mains. Okay, that when nitrobenzene is converted into aniline or reduction is being done, then how many electrons are being transferred? So you can clearly make out from +3 to -3, how many electrons are transferred? 6 electrons. Okay. Now, sometimes instead of using electrons, see this reduction is usually done by tin in HCl. So when I take tin in HCl or iron in HCl, this will give away 6 electrons. But instead of giving like an electron, it will give as a nascent hydrogen. That means an hydrogen which does not carry any charge. So 6 electrons, which means they are equivalent to speaking as these are 6 nascent hydrogens. So question could be either in terms of nascent hydrogens or in terms of electrons. Okay. In either format it is been asked, you should know what is the answer. Okay. So remember from here +3 to -3 charge change of by 6 electrons. Next, Br3O8. Br3O8 basically structure based where we have 3 bromines connected back to back, and then we have all the oxygens making a double bond round with bromines available like this. So here if you notice the oxidation state, because bromine is losing on 3 sides here, that makes it +6, and here also bromine is losing on 3 sides here, that makes it +6, and here is bromine losing on to 2 sides here, that makes it +4. So these are individual oxidation state of bromine. Okay. So if the oxidation number is asked, it is 16 by 3. Next, suboxide. Suboxide structure is like this, where we have oxygen connected to carbon, connected to carbon, connected to carbon, which is eventually connected to oxygen. This is called suboxide. In suboxide, you know that based on the electronegativity, this oxygen will have -2. This oxygen will have -2. While this carbon will have +2 because it is lost, and here it is +2. And this carbon will have 0 because it is both surrounded by same elements of same hybridization. Okay. So in suboxide, oxidation state of carbon, there are two oxidation states, 0 and +2. Again, this is a JEE question, everybody. These are multiple correct questions asked. What are the possible oxidation states existing in suboxides? So answer is 0 and 2. K3CrO4 is an old JEE question where you need to figure out only based on structure. So here, how the structure is, basically chromium has, structures this way, like this. There are two structures proposed. Okay, there are two structures proposed. One is like this: 1 2 3 4 5 6, 1 2 3 4 5 6 7 and 8. All 8 oxygens connected to chromium. This was one structure which was proposed, making everything into a peroxy group, like this. Everything into a peroxy group. Clear? So if all of them are being peroxide and overall charge being -3, because potassium will be separated as 3K plus. And now if you notice the oxidation state here, so X plus all 8, which has -1 charge, overall equal to 3. So X will be +5. So the oxidation state of chromium here is actually +5. Got it? So everybody, please check the given compounds again. Okay. See, the other proposed structure was like this. We have chromium with 6 connections here, and all 6 have oxygens here, like this. Got it? And other this 6, out of this 6, there are 2 oxygens which will have O minus and O minus, like this. Okay, clear? And rest of them were simple oxides with having this as you know plus -3 oxidation state. Okay, so if this is how it was, you can see this oxygens, here we will have -1 charge. Now check out on the chromium here. So this is another way of looking at it, that chromium will start getting electrons from these oxides as simple oxides, 4 of them being simple oxides, and here another 4 being peroxides. So X -8 and -4 overall equal to -3. Got it? Because these two are compared to be as an oxide here. So 4 of them will have, sorry, 4 of them will have -2 charge. Got it? So they would have -2 charge, and overall will have how many? -3 charge here. So that makes it +5. This is another way of looking at it. Clear? But the old JE solution, this was given. So this is more accepted form. So I've exhausted as many, structural based redox which you need to learn. Got it? Beyond this, there hasn't been any question asked in JE so far. Okay. So in all these years, if you notice, every question that has been asked, which is structure based, we have discussed it already. Right. Shall we go ahead, everyone? Right. See. Let me just give you an introduction of what exactly is an equivalent for us today. Okay. Next class, it's all about that. See. The mass of one equivalent of a substance is called as equivalent weight or equivalent mass. Equivalent is more, similar to that of moles. So how we define the mole, mole was just a number, correct? Same way, mole was also defined as a formula, that is weight of a substance divided by molar mass. On similar lines, equivalent is also a number which can be defined as weight by equivalent weight instead of molecular weight. If at all you do something called an equivalent weight, then we call this as equivalence. So number of moles and equivalents are very, very close to each other. Okay, they look very similar. And how do we get this equivalent weight? Because molecular weight, we know that, absolute mass for 1 mole of a substance. But how much is the equivalent weight? How do we get that? Equivalent weight can be calculated as molecular weight by n factor. That means there is some factor which I need to divide with the molecular weight so that I can get equivalent weight. Okay. Now, what is this n factor? How do we define that? See, it depends upon this basic definition of equivalence. You know what is the basic definition? That it is the mass which either combines with or liberates. Either it should combine or liberate 1 gram of hydrogen gas or 8 grams of oxygen gas or 35.5 grams of chlorine gas. This is by definition. Okay. That if I take a substance, I try to combine with either hydrogen, oxygen, or chlorine, or it is already in the form of oxygen, it is already in the form of chloride, it is already in the form of hydride, then maybe on heating it is giving away some oxygen, on heating it is giving chlorine gas, on heating it is giving hydrogen gas. Then what do you need to check? Either while combining or while liberating, if I take if I take a molecule, I mean, if I take some amount of substance, and that substance is giving away 1 gram of H2, or if it is accepting 1 gram of H2, then that particular weight it is accepting is called as the equivalent mass of that substance. Clear? By definition, I hope you understood. Practically, I'll tell you as we go ahead, I'll make you realize why equivalent weight is so important. Okay. What is that practical significance is? Okay. Clear? I hope all of you understood by definition. See, here, let me apply that as a part of definition in this case. Okay. Do it simultaneously with me, everybody. Okay. So suppose I'm just trying to apply that as a part of definition. What does this mean? See, if at all in this uh, uh, in this balanced equation, what does this suggest? As per balanced equation, the coefficients will always represent mole, correct? Which means if I use 2 moles of magnesium combined with 1 mole of oxygen, I'm supposed to get 2 moles of magnesium oxide, right? Now let me put the same uh, understanding in terms of weight. That is, 2 moles of magnesium is equivalent to 2 into 24 grams, which is 48 grams, correct? And 1 mole of hydrogen, which is 2 into 16, which is equal to 32 grams. So we're talking about 32 grams. Then combining these two, how much should I get? I should get 80 grams here. Got it? I should get this as 80 grams. Then my objective is to figure out what is the equivalent mass of magnesium. So to find out equivalent weight of magnesium, I need to know what is its molecular weight divided by some n factor. And you see, molecular weight of magnesium here is, 24 divided by how much is the valency factor here. Got it? This is what I need to figure out. Okay. But instead of directly finding out this, we know one thing, that is what is the definition of O2. I mean, sorry, what is the definition of equivalent weight? That is 8 grams. How much will it combine, isn't it? So now you notice for 32 grams, if 48 grams of magnesium is combining, if I take 8 grams of oxygen, then how much amount of magnesium will it use to combine? So that is 48 into 8 divided by 32, correct? So which is equal to 12 grams. Got it? So this 12 grams implies the equivalent mass of magnesium. So equivalent mass of magnesium as per the definition is supposed to be 12 grams, which means n factor for that has to be 24 by 12, which is 2. Have you noticed this is same as charge oxidation, sorry, same as oxidation state of magnesium. So that's why oxidation state plays a vital role in deciding these n factors and thereafter deciding what is the equivalent weights. Clear, everybody? I hope all of you have written that. Let us put the same way for zinc also, everyone. Let's put the same way for zinc as well. Okay. So here again, if I have to put the definition, it is with respect to the hydrogen that it is able to release. Got it? See, the atomic weight of zinc is 65. So 65 grams. Got it? Now notice it is 1 mole is to 1 mole. That means if I take 65 grams of zinc, how much amount of hydrogen will be released? 2 grams of hydrogen will be released. 2 grams will be released. Okay. And as per the definition, I need to check out for 1 gram. So for 1 gram, how much amount of zinc is being used? So therefore, again, equivalent weight of zinc will be equal to 65 into 1 divided by 2. Okay, clear? So how much we are getting here? 32.5 grams. So this is the equivalent weight. So that makes, what is the valency factor now? Valency factor is molecular weight by equivalent weight. So it is 65 divided by 32.5, which is 2. So 2 is the valency factor here. Done?
तो वैलेंसी फैक्टर क्या है?
Pardon? Can you repeat it?
सर व्हाट्स वैलेंसी फैक्टर?
Valency factor. See, valency factor is the value that you have to uh, divide it to get some equivalent masses of the element. Dekho, let me put it in a simple example here. You can see number of moles will be equal to given mass of a substance by the molar mass. This is what is the definition is. and while number of equivalents will be given mass upon the equivalent mass. And equivalent mass can be written as molecular mass by n factor or valency factor. So therefore, given mass by molar mass is nothing but number of moles, and number of moles into n factor is what we're getting it as equivalence. So this is an important formula that we will be learning a lot. Equivalence is equal to number of moles into n factor. Got it? Clear, everybody?
Yes, sir.
Okay, right. So this is how much you need to know. This is from the first session. It gives an introduction towards what is equivalence.